Okay, so yeah, so there's a bunch of stuff that we've said about Green's theorem. Oh, before I get into the math, real quick, I just want to let everybody know I worked all weekend on grading the exam, and I got most of the grading done, but not all. I have one page left to grade. I am highly confident, knock on wood, that I'll finish on Tuesday. Today I'm teaching all day, but I'm highly confident I'll finish on Tuesday. So heads up, be on the lookout for grades on Tuesday. Okay, so there's a bunch of things that we said about Green's theorem, different points of view about it. There's this accumulation feature that I think is really important to understand, right? I mean, Green's theorem's a formula, but it's just a magic wand unless you understand what is it that is the accumulating quantity and how is it that, in fact, this seemingly purely algebraic, how is it that it has this mysterious feature of accumulation? Deep down, that's what the theorem really is, my humble opinion. Then there's this density point of view about it, that, Green's operator, the integrand in the resulting theorem, it's a density. Pretty literally in the, density, concept of density writ large, that any sort of accumulating quantity per any notion of size. And so Green's operator is circulation density, right? And as such, I think that's also a really important point of view. So what I want to start with today is the observation that this is not the first time we've seen such a theorem. In fact, the fundamental theorem of calculus has both of those features. The fundamental theorem of calculus certainly can be viewed as an accumulation theorem. There is an accumulating quantity that is computed by the fundamental theorem of calculus, and it does so with a corresponding appropriate notion of density. So let me give you that sales pitch. The accumulating quantity is what I like to call change. And if you'd like, you can, just for the purpose of emphasis, you can think of this as a output change, which I hope will become implicit, as we continue this conversation. So denoted by delta, which I think is a pretty reasonable choice. We use this to represent change in other contexts. So this is the accumulating quantity. Change, output change, accumulates. And I represent that in the algebra here like so, but let me just try to make the pitch. How could it be that change accumulates? Easy example, relatable example. Think about how your height changed as you grew up. Between ages 5 and 10, your height changed by some amount. Between age 10 and 15, your height changed by some other amount. How much did your height change between ages 5 and 15? Well, the sum of those two changes, right? It's very clearly an accumulating quantity if you think about it in those terms. So this formula, f of x2 minus f of x1, aka change on the interval from x1 to x2, that is an accumulating quantity. Okay. All right. So next observation, and I think this is also a pretty reasonable, just, if you look at it the right way, pretty reasonable point of view. Let's look at a little piece of change and how we compute it. And of course, we all know the fundamental theorem of calculus, and you know what the punchline, the answer is. It's integral f prime dx. Old news. So how would I interpret this thing? F prime. Now, y'all have got a million interpretations already. I understand, of course, right? And there's nothing wrong with those. I want to take a different point of view here, whose purpose is to make sense in this context, to contribute to the point of view we're trying to develop here, and that is, and it's a density. Right? Now, the more standard points of view on the derivative are slope of a tangent line to the graph. That's the big one, right? Everyone thinks in terms of velocity, if you're talking about position as a function of time. I've heard an economist one time, I think this is a very elegant description of a derivative, sensitivity. Right? If you change some input parameter by some amount, then the output parameter changes by some other amount. And so the relationship between the output change and the input changes. So I think it's a reasonable point of view, sensitivity. So 3 at least, and I'm sure there's others, right? But I'm adding yet one more, and that is let's think of derivative as being a density. after all, if you think about it, and let's come down to this picture here. I'll try to fit this all on the screen here at the same time. What does derivative look like? Well, it's the, you draw this little picture here and rise over the run, right? And I point out that the rise is output change. It's the accumulating quantity in question for this theorem. The run, that is the denominator, you can think of as literally being a little piece of size of that little piece of the domain. Right? Went too far. So, size. So, sure, you can think rise over the run and therefore slope, or you can think distance per unit time and therefore velocity. Yeah, lots of different points, but you can think of it instead, and for these purposes, this is the way to think about it, accumulating quantity change per unit size in the domain. And quantity per unit size is a density. So I know it seems weird, but I want you to consider trying to digest this yet additional point of view on derivatives, because I think it'll really help trying to understand, for example, Green's operator. If you can think of derivative as an accumulating quantity per unit size, then that might help you kind of wrap your brain around the idea of thinking of Green's operator as being an accumulating quantity per unit size and therefore a density. Anyway. All right, so we've seen this concept of an accumulation / density theorem previously in the form of the fundamental theorem of calculus that y'all have seen long ago. I want to make another observation here before we go on, and that is you can think of this then, right, aka change density, as an indicator of where this accumulating quantity is in your picture. Right, now here's a plot of a function that is constant-ish for a little while, and then it increases, and then it kind of levels off, constant-ish again. And where is change in this picture? Well, the total amount that the function changes over, between a and b is right there, f of b minus f of a. There it is, right? But where did the change really happen? I mean, this function, it started off at one value, it ended up at another value, so the value of the function changed. Where did it change? And the derivative points right at it. So looking at this picture, the derivative is positive at these points on the graph, indicating that this is where the function actually changed. Now, is that how we measure change? Not most of the time. Most of the time, if you want to know how much the function changes, you look at the endpoint, and you look at the starting point, and you look at, again, the value of the function in the one place minus the value of the function in the other. You typically think of change as happening, correction, you compute how much change has happened on the boundary. But I don't think anyone would be inclined to say that that's where the change actually happened. We've got a graph right here looking at us, showing very visually easily that this is where the change actually happened. The change happened in the interior, and the derivative tells us how much the change is happening. So the derivative here, you can see, well, I just look at the derivative at that point. It's kind of steep there. There's a lot of change happening at that point. Whereas by comparison, over here, there's a little bit of a slope. It's not a lot, but there's a little bit of change happening there, but not as much. Because f prime is lower at that point, f prime is higher at that point. So f prime, aka the integrand, aka our density, tells us where the accumulating quantity is happening. All right, so easy example. And the purpose of this example here is just to, again, set up an analogy that we're going to extend to Green's theorem and the two-dimensional divergence theorem in just a moment, right? So this is a silly example, so bear with me. Trivial arithmetic. This function over this interval changes by a total amount of 9. where is more, that change of 9 is more happening at this point, where x equals 1, or is more of the change happening at this point, where x is equal to 2? I mean, there's different amounts happening at different points. Where is this total change of 9 more so happening? Which of these points? And, well, again, so easy answers. The easy answer is that this formula, the derivative, right, f prime, tells you how much, in some sense, how much change is happening locally near that point. And it's pretty easy to see that the bigger value of change density is where x equals 2. So, and you can see it in the picture, this is where the slope is greater. More change is happening where change density is greater. Now, again, perfectly obvious, nothing new about this other than the language that I'm using, right? I didn't say slope of the tangent line, I said change density, right? So, different terminology, but as mathematical concepts, I hope this is all boringly obvious. Okay, so the reason that I like analogies is because they give insight into the other, right? So we have a good understanding of the derivative and its relationship to the fundamental theorem of calculus. So now let's take this density point of view on the derivative and use that to help us get some insight into the density point of view of Green's theorem. And here we go. So let's look at circulation. I have just a sample vector field drawn here. Let's not get into algebra just yet. We'll do that in a few minutes. Here is a boundary on which I can talk about computing a circulation. Right? So you might say I compute circulation around the boundary of this rectangle by going along that purple path oriented as indicated. That's how circulation is computed. This is where you measure it, right? You measure it there on the boundary because, again, that's just the formula. Just like change, we measure change by looking at the boundary. That's just the formula. But where's this circulation really happening? And I've made this pitch before and it seems sort of like hocus pocusy, that even though we compute it on the boundary, it's actually happening in the interior. We should think of it as a quantity distributed over the interior, and it kind of seems a little bit of a stretch, right? But you can really see it happening by looking at, let's, for example, consider a little, let me use orange again. Imagine that this vector field is the flow of a little river, water in a river, and imagine now that I've got a little leaf that's fallen down and is floating in that river and is right, okay, well, let me try that again. Let me just do this. There we go. There's my little dead leaf, and it's floating down the river, and look, it's being pushed by the same amount on both sides. I wouldn't expect any significant amount of actual rotation either way for this leaf. It's just going to pretty much just flow right down the river, we would expect, right? Whereas, by comparison, you know what, I'll just leave that there. By comparison, if I were to look, let's say here, right, well, it's being pushed harder on that side than it is being on that side. I would expect this leaf here to be kind of spinning around kind of that way. Because thinking about the way that leaf rotates gives me some sense of what we should call the circulation at that point in the flow of the river. Right? So if you were to compute Green's operator on this vector field, what you would find is that Green's operator would be positive in this gray region here, and Green's operator would be 0 in that region up there. And likewise, by the way, 0 in this region down here as well, because again, dead leaf being pushed harder on both sides, but equally harder on both sides. So Green's operator, by virtue of where Green's operator is large, tells you where the circulation's happening. Where is this? Again, we measure circulation on the boundary, but that's just the symptom. That's just where you notice it. Where is that circulation actually coming from? That circulation's actually coming in this range in there. Everybody buy it? You can make a very analogous arguments in the 2D divergence theorem, right? So let's think about flux. How do we measure flux, and where do we see flux? Well, you see it on the boundary, right? Outward-oriented boundary flux. I mean, it says it right there in the name, right? That you look on the boundary to see outward-oriented boundary flux. Is that where it really is? Where is actually this outward-oriented boundary flux that we're detecting on the boundary? Where is it actually coming from? Well, it's definitely not coming from, for example, color choices. It's not coming in the vicinity of that little region. Let's think about that little blue region. In that little blue region, the in and the out are kind of the same because the vector field is constant. There's just as much fluid, whatever fluid this is, there's just as much fluid flowing in as there is flowing out. There's no boundary flux happening there. And if you were to compute divergence in this region here, you would find divergence to be 0 in that region. And likewise 0 in this region. But if you were to look over here, if you were to look in this general vicinity, notice that, oh yeah, right. Okay, let's see here. Yeah, so we have less fluid going in and more fluid going out, because in that general vicinity you can see what the vector field's doing. The vector field's getting larger as you move to the right. So there's more flowing out than there is flowing in. In the net, there's positive boundary flux happening in this vicinity. And 2D divergence would be positive there. So the value of the divergence is telling you where the divergence is actually happening. Yeah, you detect it on the boundary. Of course you do. But where is it actually coming from? Where is it really? It's in the interior where the divergence says it is. So in the same way that we used the derivative here to numerically quantify that there is more change happening in this vicinity and less change happening in that vicinity. Likewise, we can do the exact same thing with Green's operator and with 2D divergence. So here you go. Here's a vector field. And that vector field, if you look in the vicinity of this rectangle, well, that rectangle has a boundary. You could ask, for example, how much circulation does that vector field make on that boundary? And how much flux does that vector field make on that boundary? And you get some amounts, whatever, right? But now I'm going to ask the related question of that circulation and that flux that we just computed, whatever values they are. Where is it actually happening? Is there more of it happening at this point, or is there more of it happening at that point? Both of those points are in these. Anyway. So at which of these points is more of it happening? Right? Is there more flux happening at 3,3 or 2,4? Now again, the first instinct is to say, well, I thought the flux was on the boundary. No, the flux is measured on the boundary. Right? Just like change is measured on the boundary here. That doesn't mean the change is happening on the boundary, right? So, okay, with that in mind, then where is the flux happening more of between these 2 points? Where is the circulation happening more of between these 2 points? And, well, you can just do it with the corresponding densities. There's your circulation density, aka Green's operator. Is that bigger at 3,3 or at 2,4? Well, easy to tell. Just compute it, and that's where it's bigger. And so there is more circulation happening at this point, 2,4. than there is at the point 3, 3. Is everybody with me? It's playing exactly the same role that the derivative played in this example. It just points to, it is literally the corresponding density, so it's telling you where this accumulating quantity is happening the most. Okay. All right, and then likewise with divergence, same story really, between these same 2 points. Where is there more flux happening? Well, flux is detected by flux density, aka divergence. So which one of these points has the greater amount of divergence? Well, we just compute divergence at these 2 points. And again, the clear winner is that value 17 is bigger than the other value 13. And so it is at this point, 3, 3, that there's more flux happening. Everybody on board? Does that all make sense? So, okay. I really like this analogy. What I love about it is the fact that the fundamental theorem of calculus is so relatable, right? It's stuff that we've been seeing for years, and we can draw the pictures. I can draw the graph, and allows me to literally see the change happening. And it's just so visually clear that it's happening in the interior, not on the boundary, right? And I think that makes this what's the word I'm looking for? It makes the Green's theorem and the divergence theorem digest easier to me. It's like, oh yeah, same thing, harder picture to draw, higher dimensional picture. I just can't draw that many dimensions very well, but it's the same story. Okay, enough of that. Okay, so we're going to move on now to section 6.3, and let's see here. So conservative vector fields. The word conservative, by the way, just means that the vector field is a gradient. And I'm going to start off by kind of expressing my reservations about this word. Why would they call it conservative when we already have a perfectly good and natural word to describe vector fields that are gradients? The word is gradient. I don't understand why they feel the need to have an additional word here. So I've always thought that was weird. But anyway, FYI, if you see the word conservative, all they mean is it's a gradient. And so that's it. Okay, so turns out there's really special properties of gradient vector fields, aka conservative. And we're going to start with the theorem called the fundamental theorem of line integrals. And it's I think it's a pretty great thing to call it because it looks so much like the fundamental theorem of calculus, even in terms of how it's written down. It looks just like the fundamental theorem of calculus. It almost seems like it just automatically ought to be true because it looks just exactly the same, right? Anyway, so the big idea, and you'll recognize this from the fundamental theorem, if the vector field that you are taking an integral of, a line integral, a vector line integral of, if it is a gradient, then the line integral can be computed by this handy-dandy formula, f of b minus f of a. Said differently, all you have to do is find this magic function, little f, that I like to call the antigradient. Doesn't that make sense, right? Think about, again, the analogy from in single variable, we would call the function playing that role the antiderivative, because it's the thing whose derivative is the original, right? So I think antigradient makes a lot of sense. Nevertheless, the more common term for this, just as a heads up, I'm going to write it down here. The more common term is potential function, which seems, I don't know, why would we call it potential function? There's a good reason. It has to do with physics. I like physics, but I don't feel like we should, in math circles, have our terminology dictated by specifically and only physics applications. So I kind of object to the term potential function, just sort of on, authority basis. It just seems weird to me. But anyway, so I'm going to say anti-gradient. You're probably going to hear potential function in other contexts. Anyway. Okay. All right. So, where does this theorem come from? We'll do an example in a minute, but I want to make sure you all understand where this theorem comes from. And again, it's another accumulation theorem / density theorem. Accumulation and density are the big ideas here. So first observation to make, this quantity that we're computing, change. F of B minus F of A, right? I was at A, now I'm at B. How much did F change, right? Very natural thing to think about. Now, to be fair, previously we've thought of change as something that happens over an interval. An interval on a single axis, a input change of a single parameter, what you might call a one-dimensional change, right? And to be fair, yes, we are looking at a different kind of change here. Here we're looking at change as we move over, a vector displacement. It's not a single parameter that's changing, right? It's an entire vector input that's changing. So it's a little different, but it remains that change still an accumulating quantity in the sense that, and I like to, my favorite metaphor here is to think about how altitude change as you move along a mountain road. If you were to look at how much altitude changes from there to there, and if you were to then look at how much altitude changed from there to there, well, when you add those up, that will tell you the total amount that altitude changed from the initial start to the final end. Right? It's just perfectly clear. Change accumulates, and you can think about this in various different ways. I like to, from an algebraic point of view, I'll point out that the positive f of x1 there and the negative f of x1 there just cancel. That's an algebraic point of view, if you like, right? But I think even easier than that is just think about, the physical metaphor. It's just very satisfying. Okay. All right. How are we doing? Is everybody all right with me so far? Okay, so we have an accumulating quantity. When you have an accumulating quantity, you can write the whole as the sum of the parts. And so let's think about the parts now. If I were to have some differential small input displacement here, given some small input displacement, how much does the function change? What is the difference between, again, going with the old metaphor, the difference between the altitude there and the altitude there? How do I measure output change in relation to input change? And now that may trigger a knee-jerk reaction, relationship between input change and output change. Right? I know I said that a lot back in chapter 2. That's what a derivative does. Conveniently, in other words, we have this pre-existing relationship. The relationship between input change and output change is dot product. You know what, that highlighted weird. Let me try that again. Dot product with the gradient. That's what you That's what you do to input change dx to get output change in purple there. Delta. And then I'm going to rewrite that a little bit. I'm going to rewrite the dx as TDS. Remember that from long ago. It's one of our alternative points of view of displacement. It's a direction and a magnitude. And now the formula kind of looks nicer, arguably, in that I can see this now as a density. I can look at output change. Let me say that differently. The accumulating quantity in question per unit size on my domain. And again, if you want to think of an accumulating quantity in terms of a density, density means quantity per unit size. Here you go. Quantity per unit size is this thing. So, density change density in the context of a multivariable function as we move along a curve, change density is gradient dot t. How we doing? Everybody all right? Alrighty. Here's a different point of view. This is just a different point of view. I find this appealing, and it's also going to be really useful later on. But for the moment, I don't want to go too far in this direction. I just want to kind of plant a thought in your mind, and that is, let's look instead of this equation, let's look at this equation, and let's think of again accumulating quantity. But this time, instead of accumulating quantity per unit size, I'm going to think of dx as being oriented size. I know that's weird, right? Just bear with me here for a minute. Oriented size, because dx, if you think about it, dx tells me two things. Dx does tell me the size. Dx tells me by way of its magnitude what that size, aka length, aka ds is, right? So, but dx also tells me more. Dx, in addition to telling me size, it also tells me the direction that size, kind of how that size is oriented, if you will. And so oriented size, I think, is a reasonable thing to call dx. And so now let's revisit the question of density, change per unit size. Well, wait a minute. Now we're going to talk about change kind of per unit, if you will. Let's not sweat the algebra. Oriented size. And I think it makes sense then to call the gradient itself the oriented density. This is just a point of view, right? I'm not proving anything here. This is just a kind of a loosey-goosey way of thinking about it that I think is helpful down the road. Gradient by itself tells you change per unit size with the understanding that, well, yeah, but you're thinking of size as a vector. We're calling it oriented size, and therefore gradient is oriented density. Yeah, whatever that's worth. And it's all over but the shouting at this point. We, step one, agreed that change was an accumulating quantity, so I can add it up. Sum whole is the sum of the parts, the chop it up, add it up along the curve. Total change is the sum of each little change that I realize as I go along the road. And from above, I have these two formulas for what change is. Change is, take your pick between these two formulas. Right. So, the first way I'm going to write down the fundamental theorem of line integrals, then, is this right here that says f of b minus f of a is an integral. I've written it in such a way that it's a line integral. I've written it in such a way that I can see the density. I can see change per unit size right there. So you can directly see in this formulation both the accumulation feature and the density feature. So that's nice. Now though, let me write it in a different way. Morally equivalent, but cosmetically different. Sort of intuition different. And frankly, a little bit more convenient to write down, right? Vast majority of the time, this is the easier way to write a vector line integral. A little bit less pen strokes, nothing else, right? A little bit more compact. And what we have here is that change is computed by a vector line integral, and the integrand here, now no longer a scalar density, now it's the oriented change density. And this is the way we have it written, of course, up here. Gradient being my integrand, fundamental theorem of line integrals says that change is computed by a vector line integral. Everybody all right? Okay. Okie dokie. Let's do one. Let's use it. Suppose I am asked to compute a vector line integral here. Now, without looking at the solution and without thinking about, what we just talked about, which of course massively telegraphs how we're going to actually solve this problem, I do want to step back and think about how we would react to this question. Let's suppose this is on an exam or something like that. How would you think about this question? And the question says compute a vector line integral, and they tell you the vector field and they tell you the domain, but even better than that, they don't just tell you the domain, they parameterize it for you, right? This part here where the parameterization is given kind of seems to be kind of nudging you to, there's that parameterization. You could just plug in the parameterization and plug and chug, right? And there's a strong temptation to jump on that and to use the given information directly, right? And by the way, you could. Nothing wrong with that. You could plug and chug, pull back through the parameterization. The problem is, and I think you can probably see this coming, don't forget that this, after all, is x, and so cosine t is going to have to go there and there in the integrand, and then this is y, and so that means that sine t is going to go there and there. You're going to have a fair amount of trig in this, not to mention that's not even starting with the fact that I have to dot product with x prime. There's going to be a trig. It's going to be a trig heavy experience, right? If you pull back through the parameterization. Okay. So the reason I bring that up is I want to make sure everybody's clear that when you see a question like this on the test, and when there is a possibly inadvertent, unintended nudge suggesting maybe that you might ought to do it a certain way, that you don't have to, right? You get to decide. Unless in the statement of the question, and if it specifically instructs you to do it a certain way, of course you have to follow the instructions. But otherwise, as stated here, for example, think about what your alternatives are and pick the easiest method, right? By all means. So in this case, even though we could take a deep breath and pull back through the parameterization, we could crank it out. Nevertheless, check this out. Much more desirable. Notice that my vector field is not just a random vector field. My vector field is a gradient. This is easily confirmed. You can take the appropriate partials and confirm that the gradient of x squared y squared is indeed our vector field f. This is not just a vector line integral of a random vector field. This is a vector line integral of a gradient. And that's what our new powerful tool is all about. Fundamental theorem of line integrals is all about computing vector line integrals of gradients. Yeah? So, sweet. F of B minus F of A, and we're done. Right? Now, there's a little bit of work to be done to figure out, well, where does this path start? Well, I plug in the initial value of t, and I see that this path starts at 1, 0, and then I plug in the ending value of t, and I get that my path ends at that point, -1, 0. Right? And so it's all over. It's really all over. This is a vector line integral of a gradient. Fundamental theorem says it's f of b minus f of a. Plug in, boom, 0, walk away, no trig other than I guess I did have to evaluate the trig function there to see where a and b were. But relatively trivial trig. This is a much better solution than the old, plug it in, pull it back. Take a deep breath and plow forward. Everybody see? Okay. Yes, question.
You could verify this by if the green operator is 0, right?
This is true. Now you're getting ahead. Yes, absolutely. But I haven't. There's a bunch of details to get to confirm that. We will get to that in a few minutes. Correction. Probably on Wednesday. Yeah. Right. How we doing? Everybody happy? Okay, all right, so that's the fundamental theorem of line integrals. Now I'm going to talk about a seemingly unrelated idea called path independence, and I want it to seem unrelated because it is a very different concept, and any relationship to other things we've discussed doesn't change the fact that as a concept, this is totally different. All right, so I'm gonna momentarily sweep under the rug how this connects to what we've been talking about, and I'm gonna start with an obvious statement, and that is, when you compute a line integral, it depends on what your curve is. Well, of course it does, right? I mean, the curve, after all, is where you're evaluating the vector field. You got to drive along that curve and evaluate the vector field as you go. So, of course, where the curve is, what the curve is, and which points it includes, is going to have a dramatic impact on on what the value of that vector line integral is. Naturally. Okay. So, in that context, with the understanding that, of course, the curve ought to matter, there is this amazing fact that for some very special vector fields, only the endpoints matter. And the curve between those endpoints doesn't matter at all. It's really surprising. And I like to start with how counterintuitive this is. I mean, I don't know. Imagine how much gas you burn in driving from point A to point B. It didn't depend on which route you take. You could go the scenic route. You could go the direct route. You could get stuck in traffic. Nothing matters. Don't worry about it. It's always the same amount of gas. How could that be? That does not track with intuition. Right? Okay. All right. So before I start talking about this property more, I want to make sure I define it precisely. I emphasize, for one thing, that this is a property of vector fields. It is, and a lot of students get confused on this. Some students think that this is a property of paths or something, or sometimes people think of it as a property of an integral. It's not. It's a property of the vector field, right? It is the vector fields that we're about to talk about here that have this property. Okay, so what is the property? The property is what I call the property of path independence, and it goes like this. Path independence says that whenever you have two curves with the same starting and ending points, then you always get the same value for the line integral between those two curves. Said differently, path independence means that this vector field has this weird counterintuitive property that only the endpoints matter and that the curve in between doesn't matter at all. Okay, is everybody comfortable with how what I've written here is a formulation of this right here? Only the endpoints matter. Everybody happy with that? Okay, all right. Now, again, we've agreed that it's really eyebrow-raising to suggest that this should ever happen. I mean, after all, the curve's gotta matter, doesn't it? Just for emphasis, let me point at an obvious, easy example where, of course, it does. And this is not a surprising example. This is the norm. This is most of the time, and it seems like it ought to be all the time. So here we go. Let's suppose I start at this point and end at this point, and here's my two paths. I'm going to look for one thing on that path. Let's think about what the value of the line integral between these 2 points is if I go along this green path. And well, along in here, the value of the vector field is 0, so nothing happens there. And along in here, I'm moving perpendicular to the vector field, so the dot product is always 0. So on this green path, it's pretty clear to see the line integral is 0 on that green path. I don't even need to write down any algebra. It's just I'm clearly adding up a bunch of zeros. On the other hand, let's look now along this blue path. And okay, well, we're still moving perpendicular along this bottom piece of the curve, and so still 0 along that bottom piece. But if you look along this piece, the curve is going up, the vector field also going up. The vector field has a significant magnitude there. That blue integral is clearly not 0, it's clearly positive. So, again, This is to be expected. Of course the path matters. Are you kidding me? That's where you compute the vector field that you plug in to compute the line integral. So it almost seems obvious that it has to matter. Okay, I think I've built up enough drama on that now. And now that I've convinced you that it doesn't seem like path independence should ever happen, let me show you an example, in fact, an entire category of vector fields that do have this property. And it's weird to think, but an entire category, and that is gradients. And yeah, I do need them to be continuous. This is a little formality, but gradient fields are path independent. So let me try to persuade you that gradients are path independent. So we're going to look at the following two curves. I've got C1 here is one curve that goes from A to B, and then I've got C2 here. That's a different curve that goes from A to B. Now they share the same starting point and they share the same ending point. And so I claim, we're going to prove this momentarily, I claim that I don't even need to know anything else about these curves. Just the mere fact that they have the same starting point A, same ending point B, it immediately follows that these two line integrals must be equal. And ultimately it boils down to the fact that they're gradients. Because the fact that they are gradients is what allows me to compute C1, or the C1 line integral that is. I can compute that with the fundamental theorem of line integrals. And I can compute the C2 vector line integral with the fundamental theorem of line integrals. Because again, same vector field F, it's a gradient. It has an anti-gradient, f of b minus f of a, we're in business. And, well, these two curves have the same starting point A, the same ending point B, and so f of b minus f of a is exactly the same expression for both of these line integrals. So, of course, these things are both equal. They're both equal to the same other expression. Does that make sense to everybody? It's so counterintuitive to me. Again, when you think about vector line integrals, you usually and frankly should be thinking about this kind of thing. That the curve ought to matter. Of course the curve ought to matter. And again, I emphasize in the vast majority of cases it does. In the vast majority of cases, path independence doesn't work. There's no path independence most of the time. But for gradients, there is. Always is. This is wonderful. very, very, very counterintuitive, very surprising. Wonderful little beautiful fact. Okay. Pausing. Questions? Real quick, what we've shown here is that every gradient is path independent. I'm going to say also true, and I don't want to go into the proof. And so, if you're curious, you can take a glance at this. But it's also true the other way, that again in the nice regularity category, continuous, every path independent vector field is a gradient. So this goes both ways in this regular category. Path independence and gradient are the same thing. It's kind of wild. Okay. Pausing? Questions? Is everybody good? All right. Okay, real quick, just an alternative way to think about this. This is not a deep point. It just kind of has to get written down. Path independence means that the C1 line integral and the C2 line integral are always the same. So path independence means that these two integrals are the same, aka it means this. Now, of course, this is just the identical statement. It means that the difference between the green line integral and the blue line integral is 0. Difference equals 0 is just another way of saying the two things are the same. But notice this line integral here integral on C1 minus the integral on C2, I can draw a picture of that. That's a curve that kind of goes around like that. Notice it's going the same direction as C1 along C1's points, and then it's going the exact opposite direction along C2's points. And that line integral, therefore, would have to be 0. So this is the alternate formulation. It's just playing around with minus signs. It's the same idea, though. Alternate formulation of path independence is that for every closed curve, the vector line integral is always 0. Said differently, all circulations are 0. Just a different way of saying path independence. And I am now out of time, and we'll take advantage of these ideas and do some cool stuff next time. See y'all on Wednesday. Have a good one.